When physicists, particularly physicists of my particular interest, talk about quantum information, they're usually talking about entanglement. There's more to quantum information theory than just entanglement. There's a lot of other things. There's quantum communication, quantum this, quantum that. I'm going to tell you about a puzzle, a paradox you could call it. This is not new. This is not new work I'm talking about. This is at least a year old. The purpose of my talk is to tell you why entanglement is not the whole story. Not the whole story for what? That light is terrible. Is this all? Okay, nothing I can do about it, I guess. I'm standing in front of the projector. Okay, good, okay. Why entanglement is not enough. Not enough for what? Not enough for understanding the emergence of space behind the horizon. Is that an important problem? Do we care about space behind the horizon? Well, I think we do. I think we're all behind somebody else's horizon. And if we can't understand what's behind horizons, I think we can't understand cosmology. We certainly can't understand black holes. So I think it's a really important problem to understand how space emerges behind horizons of black holes. Now, emergence of space behind black holes is really pure emergence. That space wasn't there before the black hole formed. It's there, assuming there is space behind the horizon, after the black hole forms. Something created it. And how do we understand that emergence of space behind horizons from a quantum information point of view? All right, so I'm going to show you a puzzle. The puzzle surprised me. It surprised me a lot. But it wasn't so much the puzzles that surprised me as it is the resolution of the puzzle. The resolution of the puzzle comes from a place which I had never expected to see in physics. It comes from some very, very deep mathematics, the deep mathematics of complexity theory. Complexity theory, how many people have not heard of complexity theory? You've all heard of complexity theory. How many people know anything about complexity theory? I'm not testing you, I know. Very few. Very few. Complexity theory has not been a big deal in physics. I suspect it's going to become a bigger deal than it has been. Complexity theory, let me tell you first of all where it came from. It came from some deep mathematical questions. In fact, if I were to trace it back as far as I can, I think it originated in questions that Hilbert originally asked about the structure, the actual logic and structure of mathematics, which progress was made by people thinking about computing. Not necessarily thinking about computing with modern computers, but the progress was made by Alan Turing, Alonzo Church, Gödel, von Neumann to some extent, and then after that a lot of people who we tend to consider computer scientists, but I think they're very deep. I think the subject is a very deep mathematical subject. And I think it's coming into physics. I think it's coming into physics in a big way. Complexity theory is usually thought of as trying to classify or quantify how difficult a problem is. How difficult is it to solve a problem? Or how difficult is it to get from A to B, whatever A and B are? How hard is it? How many steps do you have to take? What's the minimum number of steps that you have to take to get from A and B to A to B? That's what complexity theory is about. It's not usually thought of, complexity is not usually thought of as a physical property of a system. I think what we're finding, or what I'm finding, I don't know about anybody else, well, I do know about a few other people. Incidentally, I should say that first of all, I should say, almost everything I've thought about for the last 2 or 3 years originated from the AMPS paradox. And my introduction to complexity was through the work of Harlow and Hayden. And so I wouldn't say that what I'm going to say is the first time complexity has appeared in physics, but I think it's the first time it's really appeared as a property of a system. Okay, so what makes quantum information different than ordinary classical information? I would say for me there are 2 things which really stand out. One of them is obviously entanglement, which you know about. It's the ability to have a system which you know everything about the system, but you know nothing about its parts. Very strange, and that's EPR. The other piece of quantum information, which I think is unusual and different than classical information, is the capacity for exponentially large complexity. To my knowledge, this was first pointed out by Feynman. I won't talk about what Feynman said, but that's, as far as I know, that's true. All right, I want to talk about entanglement first. First, entanglement and entanglement and the connectivity of space. That's where I want to begin. All right, so let's begin. I assume there's been some lectures and everybody knows a little bit about the Ryu Takayanagi construction for talking about entanglement in anti-de Sitter space. If not, close your eyes for a few minutes and I'll just remind you of some facts. The idea is that if you're interested in the entanglement between two regions, either of bulk space, but near the boundaries of anti-de Sitter space. Let's forget these little lumps that are here for a moment. If I'm interested in the entanglement between two regions of the field theory describing the boundary of anti-de Sitter space, then the rule that these people invented, and which seems to work very well, is to take a surface that is, I guess the word is homologous to a piece of the boundary, and then deform it until you find the minimal piece of the surface that's homologous with this piece. I don't know what homologous means, quite honestly, but you move it. You move it until you find the minimal surface that's anchored in the place that you're interested in, and the area, or in this case, for 2 + 1 dimensions, the length of that minimal surface is the entanglement entropy between the two sides. Now, what would happen if you had a pair of lumps? Now, these lumps, of course, I'm going to think of as black holes, but suppose you had a pair of lumps in the geometry, and imagine those lumps are not entangled for the moment. Then those lumps, if they're not entangled, do not contribute appreciably. Let's suppose they're quite near the boundary. They don't contribute appreciably to the entanglement between the left side and the right side. And in fact, you can see that by taking this curve and homologing it, whatever the right word is, and you just pass it over these lumps, and you pass it over the lumps, and you find pretty much the same entanglement entropy that you had before you put the lumps in. But what if these things are black holes for a moment? Well, they don't have to be black holes, but let's suppose they are black holes, and let's suppose they are highly entangled. Black holes are classical geometry, and it would be nice if this rule could be generalized to the case of a pair of entangled black holes, and it can be. It can be, but only if you believe that the entangled black holes are connected by an Einstein Rosen bridge. An Einstein Rosen bridge is a non-traversable wormhole. It means a connection in space, a short circuit through space. I cannot draw this so that it looks short, not on, unless I fold it over the drawing, but it's supposed to be short. And the idea now is that if you take your surface and now doing what is appropriate for homology, moving it over to here, it gets stuck. It gets stuck on the mouth of the wormhole here. And if you try to pull it until it's as short as possible, you'll pick up an extra contribution, the extra contribution being the area of the wormhole. What is that extra contribution? It's the entanglement entropy, the additional entanglement entropy, because you had two entangled systems here. This is intended as a kind of demonstration, not a proof of course, that two entangled black holes have a hidden behind the horizon connectivity, and that connectivity is called an Einstein Rosen bridge. That is the principle of ER equals EPR, Einstein Rosen equals Einstein Podoslky Rosen, that Juan Maldacena and I wrote about a couple of years ago. Okay, now how do you make entangled black holes? Can you make entangled black holes? Well, yes, of course you can make entangled black holes. You can make entangled anything. But there's a couple of ways of making it that are interesting. The first way is pair creation of black holes. Now that's of course a crazy process, so we can't do this in the laboratory, but theoretically it should be possible. A pair of charged entangled black holes created by the Schwinger pair production process, In a strong electric field, a pair of charged black holes can be created of arbitrary charge and mass, and when you work out the geometry of it, there's an instanton for it, when you work out the geometry for it, indeed you find that the geometry contains a wormhole connecting them, number one, and number two, you find out that the creation probability is only consistent if you assume the two black holes are maximally entangled. Maximally entangled or highly entangled wormhole. Now, there's another way you can make maximally or highly entangled, let's not worry about maximally entangled, highly entangled black holes. And this is highly quantum mechanical. I can't draw you a geometry that goes with it entirely, but it will go something like this. Start with a pair of clouds of particles that were Alice's and Bob's shares of entangled bell pairs. Each red connected by a black line represents a bell pair. Alice has half of them. Bob has the other half. They take them far, far away from each other, being careful not to spread the entanglement out into the environment. And then they collapse. Each one collapses their share. When they do that, they create two entangled black holes. I will assume that when black holes are created in this manner, that they do contain Einstein Rosen bridges of this type. So let me draw you another picture of what an Einstein Rosen bridge looks like. This is an embedding diagram. An embedding diagram is just space, trying to show the geometry of space. Here I have two sheets. Now these could be two distinctly different sheets of space in a world which has two distinct different spaces, but it could also be two regions of space which are far apart. In other words, which are connected, but which I haven't drawn the connection, the exterior connection. They could be 10 billion light years, well, let's say 8 billion light years away from each other. 8 billion light years away from each other, but if they're entangled, there's a short circuit. The short circuit or short connection between them. And for a particularly simple form of entanglement, particularly simple form of maximal entanglement, the way the geometry is entangled is that the horizon of the left black hole and the horizon of the right black hole are identified and touching each other. Here's the Penrose diagram that goes with this. The Penrose diagram is the right side black hole, the left side black hole. Time goes up on both sides, and the slice through at time t equals 0 is this over here. Here are the two horizons, the horizon from the left, the horizon from the right, the horizon from the left, and they touch at the center. That's the Penrose diagram describing this black hole here. Okay, this is the basic content of the ER equals EPR proposal, and I'm not going to try to defend it any further, we're just going to assume it. Okay, now what's really interesting is not, to me, what's really interesting is not just this connectivity here, but by virtue of the fact that these two systems are entangled, a whole new world of space occurs behind the horizon of both black holes. That's what we believe, that the two entangled black holes here, by virtue of their entanglement, even though they're completely non-interacting, they have no interactions between them, the only connection between them is that they're entangled, nevertheless, it appears that a region of space is created behind them, and that's the emergent region of space that I want to try to understand. How that happens and how you describe it.
Entanglement implies this bridge?
Yes.
Is that what you're saying?
That's what I'm saying. That's what I'm saying.
So if they were not entangled, what would it look like?
Ah, good. Then you would just have two. Let me come to it. I've drawn it on the blackboard. I've drawn it on the blackboard here. Next slide will not be a slide. I forgot to put a slide in, so I've drawn it on the blackboard. I put it over there and over there so everybody can see it. But let me proceed for a moment, and I'll get to that. Okay. Now, let me take this diagram, this Penrose diagram, and slice it by a series of slices representing different times. Of course, there's an infinite number of ways to do this. I want to choose, first of all, I want to choose a gauge invariant way, a geometric way that doesn't depend on coordinate slicing, that doesn't depend on coordinates in any way. that's entirely geometric, and which is smooth and which stays away from the singularity. There's a number of nice ways to construct such nice slices. Joe has called them nice slices. He says I call them nice slices, but I don't know who called it. Joe, did you call them nice slices or did I? I don't know. Nice slices mean they stay away from the singularity and they cover the whole space as Cauchy surfaces, a series of them. Here's a way to do it. You anchor the slices on the boundary of the anti-de Sitter spaces, on the two boundaries, you anchor the slices at a time t on both sides, and then you look for the maximal volume slice that connects them. Now you may think you overheard wrong that I should have said minimal size slice, but this has to do with the Minkowski signature that the sort of the minimal slices are really maximal. It's just a funny sign in the Minkowski metric. So let's call them just the stationary slices that connect these points here. And look what happens as you go from t equals 0 further in time. The slices, and in particular the portion of the slices inside the black hole, gets longer and longer and longer. Something's going on that is not stationary. Something is growing with time, and the thing that's growing in time is the interior of the black hole. That's despite the fact that the two black holes are in exact thermal equilibrium. We're used to thinking that when a system achieves thermal equilibrium, nothing happens after that. It's just stuck. It's the end of the story. These two black holes on the outside are in perfect thermal equilibrium, and yet something's growing. And classically, it's growing indefinitely. It grows to an infinite volume. This is, of course, the Einstein Rosen bridge between these two regions here. Okay, so let me show you another way of drawing it. There's the Einstein Rosen bridge at t equals 0. Right? Slice right through the middle. The two horizons are touching each other. What it would look like if you took this series of time slices would just look like this. That's my, that's my trick for showing you how the Einstein-Rosen bridge evolves with time according to this rule. What's that?
Does it shrink?
No. No. It does not shrink. It does not shrink. You're talking about the width of it? No. It does not if you use these slices. If you keep away from the singularity, it doesn't shrink. Right, it does not shrink. And in fact, the area of it at any time is essentially the black hole entropy. Right. For people who like tensor networks, this is probably the nice slice to put the tensor networks on. But okay, so what does it say? This says that Einstein-Rosen bridges grow with time. You can calculate how they grow, how their volume grows as a function of this time that it's anchored at. And you find out that the volume, the time derivative of the volume grows as the area of the slice. The area of the slice is proportional to the entropy of the black hole times the Newton constant, and so you get some sort of growth pattern that's governed completely by Einstein equations. The paradox here is that something is growing, but the black holes are in perfect thermal equilibrium. What quantity in the holographic dual description of these two black holes, the two field theories on the boundaries here, what quantity in the holographic dual continues to grow long after equilibrium? It is not entropy, and there's no form of entropy which grows after that. There are various different kinds of entanglement entropies. This horizontal entanglement entropy, which means the entanglement between the left and the right side. There's vertical entanglement entropy, which means the entanglement between the upper half and the lower half. That's something that was computed by Maldacena and Hartmann. All entropies sort of stop increasing at a time which is very short. The time being roughly the anti-de Sitter radius, and certainly by the scrambling time, which is a very short time. If you've never heard of scrambling, it's okay, it's just a short time. The entanglements have spread as much as they're going to spread. Nothing left to happen. It's reached thermal equilibrium. But yet, it looks like the geometry is telling us that something gauge invariant is happening long after equilibrium. To me, this was a radical surprise. I didn't understand it for a long time. I think I understand it now. What is the quantity that's increasing? Well, I think it's computational complexity. So what is computational complexity? As I said, I first learned the little bit that I know about the subject by reading the paper by Harlow and Hayden, and then piecing a few pieces together for myself, and then getting together with Scott Aronson, who explained the rest of it to me. And I'm a complete amateur at it. Okay, let me begin with a classical example. The classical example begins with the cellular automaton. The cellular automaton, here's a cellular automaton. The cell can either be red or white. And there are two simple states. When you think about complexity, the first thing to get straight is what you mean by simplicity. Before you can talk about complexity, you have to talk about simplicity. What's the simplest state that you can think of for a cellular automata? Well, the simplest thing I can think of is that all the squares are white, or all the squares are red. I can state it in 3 words, all the same. So that's simple. Okay? There's some rules for the cellular automata. I don't care what they are right now. Let's just assume they're more or less such that at each step of the cellular automata, only a small number of bits or a small number of cells are simultaneously involved, and nothing more than that. All right, the cellular automata evolves, and eventually it produces a state which is in some sense more complex. It's harder to describe. And there are many of them that look more or less the same, but it's just a state, but in some sense it's more complex. How can we quantify the complexity? So I'm going to suggest now that we quantify the complexity by the following rule. We first identify a simple process. We have a simple state, and now a simple process. And a simple process should mean a process which involves a small number of bits simultaneously. What's the simplest process? The simplest process is a flip of a bit, a flip of a cell. White goes to red, red goes to white. That's a reversible process. I'm interested in reversible cellular automata. So this is a simple process. I have the idea of a simple state and a simple process. And we can just define the complexity to be the minimum number of simple steps needed to get to the configuration. That is in some sense how hard it is to get to this configuration from a simple configuration, the minimum number of steps. Now we're not interested in the number of steps actually taken by the cellular automata. The cellular automata might go some crazy route to get to this configuration. The complexity of it is not defined by how long the cellular automata takes to get to that configuration. It's defined by what is the minimum possible number of steps that could have gotten you to this configuration. And this definition is fairly standard. Okay, what's the maximum possible value that the complexity can have? Well, it's clearly n over 2. There's no configuration that requires more than n over 2 flips to get from a simple configuration to a complicated. Oh, I forgot to answer your question. And I had those pictures on the board. I'm sorry. We'll come back to it. Obviously, the maximal complexity is about order n. And I also want to point out to you the maximal, n being the number of cells, of course. The maximum entropy is also order n. So it looks like complexity and entropy are simply related, very similar kinds of things. For example, if I subject the cellular automata to some shaking and bring it to some equilibrium, equilibrium would mean configurations which maximize the entropy. They will also maximize the complexity. And incidentally, almost all states have maximal complexity and maximal entropy. So it seems that classically, at least in this kind of framework, there's not much difference between complexity and entropy. Now that's very misleading when you come to quantum mechanics. So let me show you why. First of all, the classical cellular automata is characterized by a bit string in binary digits. If I had 1,000 bits, I could easily lay out a bit string on a piece of paper to represent the entire state of the 1,000 bits. It would take about half a page. Right? Quantum mechanically, each one of the classical states is a basis state. It's a basis state and which we are allowed now to superpose. So we can consider any superposition of these states There are 2 to the n of them, and so the general quantum state is characterized by 2 to the n complex numbers. That's a lot more than here. This is what bugged Feynman. Why quantum mechanics is so hard? Because just to write down the wave function of 400 qubits would fill the universe if you stuffed it plunky in density full of bits of information. Okay, so in some sense, quantum states are more complex. Let's go now and try to define carefully what we mean by the complexity of a quantum state. First of all, again, we start with a simple state. A simple state means unentangled. All right? Unentangled, the simplest unentangled state would be all qubits. Now I'll use the term qubits, all qubits aligned. What's a simple process? Well, there are single qubit unitary operators. They're called gates. A single qubit gate that acts on only one qubit, but you can't get very far with single qubit gates. Why not? You can't create entanglement. So there's a very tiny fraction of states that you could get to by single qubit operators. But with 2 qubit operators, 2 qubit gates, 2 in, 2 out, unitary, you can pretty much get to any state. When I say pretty much, there are some epsilons and deltas that you have to be careful about, and details count. But still, it's true that you can get to arbitrarily close to any state by a sequence of 2 qubit gates. All right? We replace the cellular automata by a quantum circuit, and the quantum circuit is just a sequence of gates. A sequence of gates between arbitrary qubits in some form. You start with a simple state, you run the quantum computer on it, or you run the quantum circuit on it, running it, applying these unitaries, until you get to the output state. The complexity of the output state is the minimum number of gates that it would take to go from the simple state to psi. Now, how robust is this definition? How robust is it against different choices of gates and so forth? The numerical coefficient in front of the complexity is not robust. What is robust is everything else but the numerical coefficient. So
Lenny, is complexity a property of a single state or an ensemble of states?
No, it's a property of a state. It's a property of a state. The cheapest way to get there, right?
Lenny, you chose a particular basis to
Yes. Complexity is basis dependent. Now, what basis do you use? The assumption here is that the Hamiltonian of a system is what is called K-local. K-local means that there is some basis in which the Hamiltonian is a sum of terms, each one involving a small number of qubits. So that's the basis that we're assuming. Okay, with this definition, with this definition, the maximal complexity is e to the, when I say e to the n, I mean exponential in n. This stands for exponential in n, not e to the n. It could be 2 to the n, it could be 4 to the n, it depends on details. But it's exponential in n. Why? Because the quantum states are so much more complicated, but the maximum entropy is still just n log 2. That means there's a vast gulf between maximal complexity of a state and maximal entropy. If you take a system and you run it by its own Hamiltonian or by its own dynamics, it could be just a quantum circuit or it could be a Hamiltonian system, the time to achieve thermal equilibrium is the time for the entropy to get more or less maximum. Let's say maximum. For a black hole, that's very fast. It takes, well, depending on how close you really want to get, there's a scrambling time, and the scrambling time is only logarithm of the total entropy. N can be identified with the entropy of the black hole, the number of bits that it takes to describe it. It's very fast for a black hole. A black hole of solar mass would come to thermal equilibrium in about a millisecond, and it has a huge, huge entropy. So it's a logarithmically rapid process. This is called fast scrambling. On the other hand, the time that it would take to achieve maximal complexity is order e to the n. That's how many steps you have to go to. So there's a vast gulf between getting to thermal equilibrium and getting to maximal complexity. You can guess now where I'm going, that thermal equilibrium is not the end of a story. Here I've made a plot. Now this is a plot of expectations, not a plot of anything I can prove. I'll talk about what can and can't be proved if I have time at the end. All right, vertically I either plot entropy of a system which is undergoing some evolution from a simple state, and I plot complexity. Entropy will max out at n log 2. There's no way that you can have more entropy than order n. That will just max out. The complexity will continue to increase for an exponential time. Now, as I said, this is difficult to prove, and I'll come back to that. But the best guess is that it increases linearly for a long period of time with a coefficient that is proportional to the number of bits in the system. Why? Well, the more bits you have, the more complex you'll get after a certain amount of time. And the temperature. And the temperature is just there because the temperature provides a rate. The higher the temperature, the faster the collisions between things and so forth. So there's a theorem called the Margulies-Levitin theorem, which basically justifies this kind of formula here. And the time rate of change of complexity, and this potentially can go on until the complexity maxes out. The complexity maxes out at an exponentially long time. So now why are we never interested in this complexity? I mean, you condensed matter physicists would never want to think about complexity. It's too subtle. It depends on these very delicate phase relations. It's very global.
It's a fine-grained quantity, right?
I've called it fine-grained in the past. I don't know what one means.
It's a property of a microstate, not of a macrostate.
Oh yes, it's definitely a property of a micro.
Entropy is a property of a macrostate.
Yes. That's right. But it's more than that. It's more than that. It's so delicate that nobody could ever use it in any practical sense. Okay, let's leave it at that. Yeah.
So I realize one of your basic assumptions is fast scrambling, but to what extent do you think we really know that all the subsystems of a black hole scramble on that time scale?
Well, I refer you to a paper by Maldacena, Schenker, and Stanford, and I'll leave it at that.
Well,
that's all I know.
Well,
that's all I know.
Do you think that's really answering the question?
Apparently you don't. Not completely.
I mean, this plot is like almost obvious, right? I mean, you just simulated it.
What's obvious to some people is not obvious to other people, but okay, right. All right, so we have two formulas. The rate of change of complexity, which increases linearly for a long time, not forever. It's important to realize it doesn't increase forever, but it increases for a long time with a, I don't know, I may have screwed up these equations, but the important thing is the complexity increases linearly with a coefficient that's proportional to the entropy times the temperature. For an ADS radius black hole, this would read area of the horizon divided by Newton constant times the ADS radius. But it increases linearly with the area in particular as the coefficient. The volume of the Einstein Rosen bridge, and I told you about the volume of it, it also increases linearly with area. And one might therefore speculate that the volume of the Einstein-Rosen bridge as a function of time follows the same law and is in fact proportional to the complexity of the quantum state. That would mean, if it were true, that complexity is not such a terribly delicate thing when looking behind the horizon. That the properties of the physics behind the horizon, the coarse-grained, just volume itself, is connected with this very, very delicate quantum quantity, the complexity. Is this a coincidence? I mean, the fact that both of them grow linearly, is there any real evidence, any stronger evidence that complexity and volume go together? All right, so here's where some recent work was done by myself, Douglas Stanford, Steve Schenker, and Dan Roberts, right? And Dan Roberts was here. Yeah, did I think your name is just someplace, Dan. I'm sorry. what Dan Roberts and Douglas Stanford did is much harder than anything I tried to do. What I'm going to explain here is something that Douglas and I did, which is a baby version of the harder thing. Okay, so what is a precursor? Let me explain what a precursor is by an analogy. Analogies are dangerous because, of course, people always draw the wrong thing from the analogy. But nevertheless, let me give you another. This is Alice's lunch date story. Alice is a quantum information experimentalist, and she has a quantum circuit. And she's going to run her quantum circuit from early in the morning till late at night, and at the end, she's going to get something out of it. Okay? But part of her protocol is that at 12 noon, she's supposed to go into the quantum circuit and flip one qubit, or do some operation that we'll call W on one single qubit. That's part of what she has to do. But she has a date with Bob, a lunch date with Bob, a brunch date with Bob. And, you know, things happened, and I won't tell you what happened, but things happened, and Alice forgot all about what she had to do. Well, at 2 o'clock, she runs back and she says, oh my God, I forgot to do my protocol over here. She runs to 2 o'clock, and she says, there's something I can do. Is there anything I can do to make up for what I failed to do over here? And Bob tells her, yes, what you can do is instead of applying W over here, you can take the time evolution operator of the circuit and apply U inverse. And it will give you exactly, U is now the time evolution between noon and 2 p.m. And if you apply this now, you'll be fine. You'll get exactly the same result. The only problem is that this operator over here is very complex. In fact, complex in the technical sense. If I wanted to generate this operator, it's a unitary operator by a series of gates. This operator would be much more complex than the symbol operator over here. Why? First of all, it involves all or many qubits. But second of all, it involves phases that might have evolved during here and here. And so Alice has a tough job to overcome the complexity of this operator here. The complexity of operators can be defined in the same way as complexity of states. How many gates does it take to construct them? Okay. What is the additional complexity that Alice has to overcome because she waited a time t? This can be calculated. This can be calculated by some quantum circuit tricks, just pure quantum circuit tricks. And one finds the additional complexity that it takes is proportional, if the system can be defined as a thermal system, if it has S times T, incidentally, S times T is a stand-in for the energy of the system. You know, S times T, dE equals TdS. S times T is a stand-in for the energy. You could use the energy here, the energy above the ground state. The change in complexity due to the extra operations that she has to do is proportional to twice St times the time delay times the time amount of time that this is the penalty that she pays for waiting a time t. But wait, this can't always be right. What if that extra W that she had to stick in was just a unit operator? If it was just a unit operator, she does nothing. And in fact, she doesn't have to do anything at the end if it was just a unit operator. So there must be no cost in complexity if W is 1. There must be a complete cancellation. What if W is just 1 qubit? Then there's a partial cancellation. All the other qubits at first don't know that this extra qubit was fiddled with. So the other qubits don't know it. There's almost a complete cancellation at first. But what happens is, here's a way to picture it. Think of the evolution of the system as a trajectory in Hilbert space. A trajectory in Hilbert space is the evolution of the system. That's U. And here's the operation W. We come in and we kick the system a little bit, and then we try to run it backward, U and U dagger. we try to run it backward. We've kicked it a little bit with 1 qubit. Had we not kicked it at all, it would just track right back. But if we kick it a little bit, it will start to track back until enough qubits have been influenced that the system says, oh boy, I've really been hit. And then chaos, simple chaos, will turn it around and make it go off in some other direction. There's a partial cancellation. The partial cancellation adds up to the following. Instead of just twice STT, you have to subtract off a piece, and the piece you subtract off can be calculated. It's proportional to the scrambling time, but it can be calculated. And that's the answer. The additional, this is the penalty that Alice has to pay. Pay in complexity and the complexity of the operations that she has to do. Okay.
Is that last equation supposed to be exact, the coefficient?
No.
T minus LABS.
Hold on, let me go back to the equation. Oh, this equation, this is coming from the Schenker Stanford Maldacena Kitaev.
LABS or the black hole radius?
Actually, this should be 1 over the temperature. It should strictly be 1 over the temperature. It's beta over 2 pi. So the coefficient is exact, it's just wrong. Okay. But it could be made right. Okay, so here's now our problem. Let's assume the black hole starts at t equals 0. It's created by some agent that creates it at time t equals 0. It could be the, an instanton creates it. What's it called? The Hartle-Hawking instanton or whatever could have created this at time t equals 0. Here's Bob's side. Here's Alice's side. Alice wants to send a message to Bob that Bob will receive after he falls into the black hole. Okay? If Bob is going to jump in no earlier than t equals 0, and Alice is going to send the message no earlier than t equals 0, she can't quite get the message to Bob before he hits the singularity. So she says, wait a minute, let me go back in time, run the system back in time. Now, it really didn't exist before this time, but she says there is an operator that I could have applied that would run it backward to an earlier time, and then apply W, and then run forward again. That corresponds to some more complex operator, not just a perturbation at the boundary here, but some sort of very complicated perturbation that she could do, and the effect of that perturbation will be to send the signal that Bob can receive.
Sorry, it still acts just on her Hilbert space?
Just acts on her Hilbert space. Isn't that marvelous?
Even though U acts on both?
Oh, no, U is a sum of 2 terms, a left and a right term. So W is a pure left object. U dagger U, the right terms cancel from that. Okay, right. All right, so what happens then is she applies a complicated operator at t equals 0, which in effect actually just creates a particle over here. But how does she do it? She uses a precursor. She does the same trick that she did when she had Bob's lunch date. She runs it backward, applies the operator, and then runs forward, and therefore sends the signal to Bob. The effect of such a perturbation, even if this is a very low perturbation, low energy perturbation, even if it's a very low energy perturbation, a blue shift occurs, and the blue shift creates a very high energy shock wave. The very high energy shock wave in here that was calculated by Schenker and Stanford about a year or 2 ago. And it is not a small effect, even though there was only 1 qubit that was modified over here. Okay. Let's go back now and take the effect of the shock wave and recalculate the volume of the Einstein Rosen bridge, how it changed as a consequence. Here it is, the shock wave goes in, this surface which is anchored at the 2 ends, we look for the maximal surface, same rule as before, but now it's been perturbed by the effect of the shock wave. We can calculate it. It's an Einstein gravity calculation. No information theory goes into it. Pure Einstein gravity. We calculate the effect of the shock wave, and we calculate the change on its volume, and the change on the volume is exactly matches the change in the complexity that would be expected by the circuit analysis of this. Same T star appears here, and this was worked out by myself and Douglas Stanford, and then a much harder version of it, much more detail, and really, to my mind, a real smoking gun calculation was done by Dan Roberts and Douglas Stanford. My name is on the paper, but that calculation scared the hell out of me, and I didn't go near it. I think I said something that might have started the calculation out, but I really did not have any contribution to the. Okay, I'm going to quit now and turn it over to questions, if there are questions. What are the implications of this? I think the first implication is that the holographic encoding of space behind the horizons is different. It's built out of extremely subtle correlations that define quantum complexity. It is not just the ordinary correlations that define entanglement and entropy. Okay? Complexity and geometry are in some sense, now strictly here I should mean complexity and volume, but in the Douglas Stanford, in the Roberts Stanford version, it's more complicated geometric details. Those details appear to be dual to aspects which could be called complexity. That the geometry behind the horizon reflects things which from the outside would be called complexity and much too subtle to ever measure, and from the inside they seem to be real geometry. The classical evolution of geometry cannot persist for all time. Complexity and therefore volume must stop growing when it gets to be of order e to the s. That's an interesting fact, that classical geometry has to break down after a time. There are questions, definite questions that I think can get answered, or they're hard ones, but does the complexity actually continue to grow for an exponential time, or might it stall? It might stall at a scrambling time, so the classical geometry breaks down at a scrambling time. What are the implications one way or another whether it stalls? They're very, very interesting. It's a problem that Scott Aronson and I have been working on. Again, I don't have the capacity to answer this kind of question. Scott has the power to answer it. In fact, it's too hard to answer. In fact, but it is possible to connect it with other questions of complexity theory. Unfortunately, not N and NP, but other similar kinds of questions. And it's possible to show that the exponential increase of complexity is equivalent to conjectures about complexity classes which are rather believable. I think they're highly believable, but at least according to Scott. All right, another question. Do we need new nonlinear rules for quantum mechanics behind the horizon? Or is standard quantum mechanics sufficient? This, I think, is not a clear story. I have no time left. I don't even have time left for the last question.
It's interesting.
No. No, I'm finished. I'm a good citizen.
So who asked the last question?
With regard to the last question, cosmological approach, it seems that the universe starts out simple, right? So someone's complex and gets simple again.
Well, I think you're using the word simple in a different sense than I am.
I'm using it in the sense of effective complexity of systems.
Well, you would call a completely thermal system in thermal equilibrium, I think you would call that simple.
That's right.
I would not. I would say this version of simplicity and complexity continue to evolve for a very, very long time after thermal equilibrium sets in. They're two different concepts of complexity. Both of them are interesting, and Scott Aronson writes about both of them.
Would it be fair to say that your definition is the same as depth?
Yeah. Well, minimal depth. Minimal depth, yeah. Depth of a circuit. Yeah. Minimal depth, that's right. Okay, so the last question was exactly what Jim raised. how does all of this connect with the growth of cosmological space? And there I don't know, but the space behind the horizon of a black hole is a growing space. In some sense, it's a cosmologically growing space, and perhaps it has lessons.
We first have a question at the back. Yeah.
Yeah, so you keep referring to circuit complexity, which is sort of notoriously difficult.
I recognize a voice, but I can't say who it is.
You keep referring to circuit complexity, which is notoriously difficult to compute.
Yeah.
In very simple circuits, you know, where you sort of...
It's very difficult.
Yeah.
Right.
So, but there are other things like query complexity, which are much better understood, where you can really prove the query complexity in many cases. Is there
How
a connection?
many questions do you have to ask the oracle?
Yeah, so I'm wondering if those might be connected to geometry in some way.
That you'll have to ask Scott, but that would be very interesting. I don't know. What I know about query complexity is just it's how many questions you have to ask an oracle, and no more. I really don't know. So it's not only a question that you should ask Scott, it's a question that I have asked Scott, and I don't know the answer.
Yeah, Lenny, when you talked about the complexity of a cellular automaton, you emphasized the fact that...
I'm not talking about the complexity of the rule. I'm talking about the complexity of the state after a certain time. Right.
So you emphasized the fact that you define complexity in terms of some minimum that was independent of what the actual evolution of the cellular automaton was.
Yes.
But in the ADS application, it seems like you're insisting that we're talking about the rule being the Hamiltonian of the gauge theory.
That's the rule of evolution.
Yeah.
Right. Now, let me give you an example. The rule of evolution is expected after very, very, very long times to produce quantum recurrences that bring you right back to the thermal field double state. Right. Do we want to say that the thermal field double state after a long time is more complex than the original thermal field double state? I don't think we do. So the time that it takes the actual machine to get there is not really a property of the state, because you can have two identical states with very different histories getting there. The thing that's the property of the state, I think, is the minimal circuit that could have gotten you there. Given the state, you can ask what's the minimal circuit that you could have gotten there, and that's a property of the state.
But aren't you relating the growth of the Einstein Rosen bridge to what happened in the time of the gauge theory?
So there's a theorem that you can prove that for some length of time, the theorem I learned from Michael Nielsen's work. The theorem says that for some unknown and unspecified length of time, that if the Hamiltonian itself is k-local, means made up out of these small chunks, then the complexity growth is identical to the length of time that the circuit has evolved. All right. So it's a statement that the most efficient way to get to simulate the evolution of a system is with the system itself, up to a time. But then short circuits can happen and do happen. Right.
All right. Joe, you had a question? No. Okay. Anyway. There you go.
I didn't understand which aspects of your story hold for generic quantum system and which are special to holography and gravity.
Oh, I think this is a generic systems. This is true of.
Oh, so
this is not
the behavior of gravity is in no way special in this story.
That's right. Well, okay. The only thing that's somewhat special is the assumption that the Hamiltonian is k-local, but not local in space.
Sure. So generic.
Right. That it's a fast scrambler.
Within that class.
That it's a fast scrambler. Yeah, I think that's right. Yeah. Now it may be that all systems which are scramblers have gravitational duals. No, he says no. So I withdraw that statement.
So are there any features that you think might be special to quantum gravity within this?
Okay, so I have to think about that. Let me get back. I don't know. I don't have a fast answer to it.
I also have a question. I mean, you talked about a two-sided situation, but if I do a one-sided black hole,
Certainly the existence of an interior is special to gravity.
Right, but what does that reflect about the system?
Yeah, right.
That's begging the question, right?
Yes. Well, yes, and I'm going to, right.
So the one-sided situation, there you can do a similar thing?
Yes,
and,
yes.
And so what does your...
Can we raise this up? I have the pictures here, but...
Yeah, but what, this, I don't know how to...
I think the whole story is the same.
But does it say how do you think this complexity story is related to the solution of the firewall paradox? Or, I mean, how do you connect it to it? Because
I'll be back here in about a week and a half or 2 weeks, and that's what I'm going to talk about.
Okay, all right.
Okay. And the answer is only partial. I can only say I think this and I think, okay, let me say what I do think. What I do think is that this expansion, which is the expansion due to the expansion of complexity, is what protects the system from instabilities. It's like an expanding universe. A contracting universe is terribly unstable with respect to create instabilities, getting blue shifted and creating nasty things. My sense of it is that the expansion, which I'm now tracing to the expansion of complexity, now if I took a completely generic state, it would have pieces in it which were expanded. Pieces were generic would be a sum. The generic, I mean, you just pick an ensemble. Mm-hmm. The ensemble would have expanding things, it would have contracting things. And so my guess is the most generic states are probably pretty singular. Mm-hmm. Those states which start simple and which can evolve for a long time, increasing their complexity, I think are protected against these kind of instabilities. That's my feeling about it.
All right.
Yes, Ted.
Yeah, all right.
Going back to the funny sign that you mentioned in the Lorentzian metric.
Yeah.
So, I mean, you could deform the surfaces that you drew there so that their volume would actually get very small and they would look pretty much the same on the diagram. In other words...
Well, you could deform them, but you could deform them right back to the to the light cone and make their volume 0.
Exactly. So
right? Or you could deform them upward and...
Yeah, so the question is, how do you interpret that in terms of complexity?
No, I'm
What's
saying...
happening to the
what I'm saying
complexity?
is I've given you you may say it's a nutty definition, okay? But I say it's a gauge invariant definition I've given you. That's all I really care about.
It is. It is.
Yeah, no, my point is that gauge invariant definitions should reflect properties of the quantum state of the CFT. If I give you a gauge invariant property of the system, that property should be encoded in the CFT in a gauge invariant way. And you don't like my definition of an Einstein Rosen bridge? I don't particularly like it, but it's gauge invariant and its size grows, so that's telling me something is growing in the CFT. That's the only way I'm really using it.
All right, one last question over here.
From your description of complexity, it seems like a prerequisite is to have at least a thermal state in black hole. But I can imagine actually if I take a 0 temperature state that has 0 or area law entropy, it can still be very complex and take a much larger number of steps. For example, if I take a spin liquid wave function,
yeah,
it could be, I'm thinking maybe it could have high complexity but low entropy. Is it possible?
I don't know. I don't think it can be more complex than the time that it actually took to make it. If you can, you want a spin liquid is for our purposes now could be in its ground state or not?
Yeah, yeah.
Is there an energy gap for the system?
Let's say a gapped spin liquid. It's composed of an exponentially large number of say classical configurations. So
well, yeah, I know.
Right, but
the ground state. Let's say the ground state is non-degenerate and has a gap.
Non-degenerate. Yeah.
Okay, then you can construct that state, I think, in a polynomial time. Why? How can you construct in a polynomial time? You can use an adiabatic algorithm to, well, you have better algorithms, but you can construct it in a polynomial time. That means a polynomial number of steps. Its complexity is negligible. Compare that with the complexity of a state somewheres in the quasi-continuum, where the entropy and the separation between levels is e to the minus s. That, I think, is exponentially complex. It would be exponentially hard to generate those states.
All right, it's time for the morning break.
Good.
We come back at 10:30.